So you, for each of the, or for both of these, you need their, the two equations. A equals P times 1 plus R over N to the NT for the first one. And then that part A equals P times E to the RT. All right, so for part A, you should have gotten $4,772.25. Remember, it's money, so we round it to 2 decimal places, and it won't necessarily tell you that. And then for continuous, you should have gotten $4,773.84. Questions? Be careful how you type things in. I would say just watch like how you do your order of operations. If you type it all the way in, like straight out, your calculator should know how to do that. But if you have one of the more simple calculator, if you're using a scientific calculator, you got to work backwards. You got to do like the 0.02 divided by 12, then plus 1, then raise it to the power, then multiply by 3,200. It should make sense logically. It shouldn't be a huge jump in money unless it's in there a lot of years, or it's being compounded really often. Other than that, it shouldn't be that huge of a jump in money. And it obviously should never go down. All right, so 3-2 is called log functions. Also something that we went over in Algebra 2, but we're going to keep going with it. So first thing we're going to talk about is what is a log function, okay? The log is short for logarithmic, and it is written as y equals log base A, in this case, of x is how that's written. I mean, that's how it's read. So if I had y equals log 2x, it's read as y equals log base 2 of x. The small subscript number is the base of your log, just like the base of your exponential function, okay? And we are going to do a couple things with this. We're going to learn how to convert from one to the other. So to go from log to exponential and exponential to log. And then we're going to learn how to graph logs. And then we're going to learn how to evaluate these. There's a lot of mental math when it comes to logs. So these questions can be relatively fast when you get questions that are just like evaluate. Which is why lazy people tend to like these a little bit because it's a lot of mental math. But you are also going to be doing the graphs of these. So first is how do I go from one form to the other? So if it's in log form, then the base on the log comes over to the other side and picks up the y, and then it drops off and leaves the x by itself. So it would be b to the y equals x. I think Miss Corey teaches like b, right? B, so the base picks up the other side, and then the exponent. I've said before, it's like a high school relationship. The pairings never stay together, okay? So if they are together in your log, they are not in the exponential, and reversed. If they're together in the exponential, then they separate in the log. The base on the exponential function becomes the lower number, or the base on the log, and then they separate. So the y would go to the other side. The x would join the log. So if I have 2 to the third equals 8, then this is the same thing as saying log base 2 of 8 equals 3. They're interchangeable. So you can go from one to the other or back and forth, okay? And it'll either say put it in log form or put it in exponential form, or vice versa like that. So example 1 says write each equation in the equivalent exponential form. These are in log form. So the 2 comes over and picks up the 4. So 2 to the 4th would equal x. For right now, we're just writing these, but obviously this is something we will eventually solve, and 2 to the 4th would be 16, and you would actually work that out. B, 3 to the x equals 9, and that's your 1 to 1 one. We would eventually work this out to make it be 3 to the x equals 3 to the second, and x would equal 2. The directions here just said to rewrite it, so we're not actually evaluating. Now we're going the other direction. Rewrite the equation in its equivalent log form. So this becomes log base b of 16 equals 4. And then log base 5 of x equals 2. So at the foundation of it, you have to know how to get from one format to the other. Questions? All right, now you're evaluating. So now we're going to actually try to find it. And notice it says without the use of a calculator. So if a equals f of x, or f of x equals log base 4 of x, and x is 64, there's two ways to do this. One is I can actually rewrite this as y equals log base 4 of 64. And long way around is convert it to exponential. So 4 to what power equals 64. Then I can change the base. So 64 is 4 to what power? 4 to the third. And then I know that this is y equals 3, or f of x equals 3 because it was an f of x to begin with. That's one way to do it. The other way is to eventually the hope is that you get so good at things like this that you can do that mentally without having to convert it. So the question is there a power I can raise 4 to get to 64? And to get from 4 to 64, we'd raise it to the third power, and that's my answer. So the faster you are at figuring that stuff out, the easier these are going to be. If you look at B, this would be log base 36 of 1/6. So again, I can set it equal to y. I can say 36 to the power of y equals 1/6. And then if I wanted to bring the 6 to the top, what would the exponent have to be? -1, good. And then 36 would be 6 squared times the y that's there, means 2y equals 1, or -1, and y equals -1/2. But again, you can avoid that whole thing by saying, what do I have to raise 36 by to get to 1/6? I know it's going to a fraction, which means my exponent has to be negative. And to get from 36 to 6, I have to square root it. And a square root is the same thing as raising something to the 1/2. So if I need to get from 36 to 6, I'm square rooting it, and that square root would be a power of 1/2. If it was a cube root, it's a power of 1/3. If it's a fourth root, it's a power of 1/4, and so on and so forth. Questions so far? All right, now you're going to use the calculator. So this time where it said, it'll say to evaluate, God bless you, log of something. Now log by itself actually means log base 10. Most of the calculators only have a log button, which means it is log base 10. There's a way to do this and change a base. We'll get to that later. But for right now, if I want to find the log on a calculator, you can only use log base 10. So if I wanted to find log of 1,000, there's two different ways depending on your calculator. If you have the TI graphing calculator, you literally just have to write log and 1,000 and hit enter, and you should get 3. If you have the scientific calculators that do not store things when you hit it, then you have to do 1,000 and then hit log. So like your phone, you'd have to do 1,000 and then hit log. So the order changes, okay? But most of you have that graphing calculator that if you do it, that this would be the order this would be the order that you're gonna do it. You would just hit log. So log of 5/2, I literally would hit log 5 divided by 2, and I get 0.39794. If you wanted to do log of 5 over log of 2, you have to either separate it out or you have to put your parentheses. So if I'm gonna write this in, I have to do log of 5 and close the parentheses because it automatically opens them for you. And then divided by log of 2. You don't have to close that last parentheses, but you should get this, 2.32193. And then if it's -3, it's going to open the parentheses. Make sure you put the leading negative. And you should get an error because there's nothing I can raise 10 to make it negative. So make sure you practice. Like if you've got your calculator out in front of you, find log of 1,000, log of 5/2, log of 5 divided by log of 2, and then log of -3. Practice all of those and make sure that you're getting the right answer. Log of 1,000 is something that obviously you should be able to do without the calculator. 10 to what power gives you 1,000? You need 3 zeros, so it's 10 to the third. All right, so this one says use a calculator to evaluate the function of the indicated value of x. -3, and it says log base 10, but this doesn't even need to be there because log is implied log base 10. So -3 times log of 2.7. You get -1.2940. It doesn't say which round to. We're going to keep 3 decimal places, which should be -1.294. Questions? All right, so these are properties that we can use to help us like with the mental math state of stuff. If you have log of any base, so a could literally be any base, and the big number is 1, that answer is 0. And you would not be able to figure it out by raising to a power, okay, or doing some sort of factor tree. You would just need to know that. So log 1, 0. Log 7 of 1, 0. Log 3 of 1, 0. If the big number is 1, then my answer is 0. If the base and the larger number are the same, then my answer is 1, right? If I had log base 3 of 3, it's 1. Log base 5 of 5, it's 1, because you would raise that thing to the power of 1 to get itself. If the base on the log and there's an exponent on the other, then the answer is just the exponent. So if I have log base 2 of 2 to the third power, my answer is just 3. So I'll show you in a second the long way around to do that on the next example, but this is the stuff that would help if you could just see that, okay? And use, like, that's straight up mental math. And then the reverse of that is if I have an exponential function and in the exponent is a log with the same base as my exponential function's base. So if I had 2 log base 2 of 3, the base on the exponential function is the same as the base on the log in the exponent, and that is also just 3. I literally ignore this whole thing and grab what you're finding the log of in the exponent. And then the last one, and this is your one-to-one property using logs. If you have a log of the same base on either side of the equal sign, then you can ignore the log and just set what's next to it equal to it. So if it said log base 2 of x equals log base 2 of 3, then my answer again would be x equals 3 because the log and the 2 are the same. So that's your one-to-one property applied to logs. Questions? All right, so let's see if we could do this again with minimal work. Log base 3 of 81 equals x. What's the answer there? 4. X to 3 to the x power equals 81, right? And 3 to the 4th equals 81. How about B? Log base 5 of 1 is x. What's x? 0. Questions? All right, let's see if we could do these with no work. A, log 3 base 3 to the power of log base 3 of 15 would be 15. That whole thing cancels out. B, log base 2 of 2 to the third. 3, it's just the exponent. C, log base 9 of 9. 1. And D, log base 3 of 1/3.
1.
So close. -1. I got to move it to the bottom, right? This is why people who hate to show work love logs. Yeah? Questions? This is where like we get to do GIM kits and stuff like that with logs because they require very minimal work. Questions? Yeah? They get more complicated, but in the beginning, nice and easy. All right, now we're going to graph logs. So a log and an exponential function are inverses of each other. Meaning if I took 2 to the x and I found all my x and y coordinates, which is what's down here, and then I wanted to find log 2 of x, the graph of that, I could literally switch the x and y values that I found from doing 2 to the x, because they are inverses of each other, and inverses we switch the x and the y. So there's two methods to graphing logs, and one is graph the exponential and then switch all the x and y's, which sometimes is simple but gets complicated when you start to have shifts. So I teach it a different way. I'm going to teach you how to take your function, you're going to rewrite it in exponential, and then you plug in for the y. So when we're graphing these, we're going to plug in for the y, because it will be a base raised to the y power. So all the things that were true about exponential, if we were comparing these graphs, the exponential are in the blue. These were our exponential functions. The one on the left, if the base is a whole number. The one on the right, if the base is a fraction or a decimal. If I switch the x and y's, they become the red functions. And that's what logs look like. So everything that was true about an exponential function is now going to be true about, in reverse, about the log function. So in an exponential function, we had a horizontal asymptote. For a log, we have a vertical asymptote. In an exponential function, we had a y-intercept. On a log, we're going to have an x-intercept. So all of those things switch. And in an exponential function, the horizontal asymptote moved with a vertical shift. On a log, our vertical asymptotes are going to move with a horizontal shift. So that's where it changes. The domain of all the, if you remember exponential, the domain was all real numbers and the range had a fix. Now it's the reverse. The range on log functions, so actually on the range on them, is negative infinity to positive infinity. And now your domain is going to have a restriction. It starts at 0 to positive infinity for the parent function, and it shifts with a horizontal shift, which means it is in the parentheses with the log, or with the x. So what was important to identify from our exponential graphs is if there's a vertical shift. What is important to identify from our log graphs is a horizontal shift. You can get the vertical asymptote, and we can get it two ways. We'll either get it from our chart or by setting the parentheses equal to 0. That's also, so that's how you find the vertical asymptote. And then you'll get the x-intercept by plugging in 0 for y, or using the middle coordinate of our t-chart, because we're going to plug in for y. This will be your x-intercept. All right, transformations work exactly the same. If there's a vertical transformation, it's happening after the log, so not inside the parentheses. And that if it's positive, it shifts up, and if it's negative, it shifts down. The most important one on logs are the horizontal translation, because it shifts your vertical asymptote. If it happens inside the parentheses, if it's a positive, it's a shift to the left, and if it's a negative, it's a shift to the right. Like everything else, a reflection on the front flips it upside down. Inside flips it left to right. A number on the front is going to cause a vertical stretch or shrink, and a number inside is going to cause a horizontal stretch or shrink. Those you will find from your points, though. The most important thing you have to identify is the horizontal translation. All right, we're going to graph it. And we're not even going to do the exponential. We're going to go straight to the log. So the first step is replace g of x with y. This becomes y equals log base 3 of x. Step 2, convert this into exponential. So what is this in an exponential function? What's the exponential function of that? Thanks, Sam. 3 to the y equals x. So it becomes y, or 3 to the y equals x. And this is why we plug in now for y, because the y is the exponent. So I do -1, 0, and 1. And I plug in 3 to the -1, 3 to the 0, and 3 to the first. What's 3 to the -1? What is it? 1/3. 3 to the 0. 1. 3 to the first? 3. And then I plot those points. Be careful because people tend to, like, when they switch it in their brains. It is still the xy. So 1/3, -1, 1, 0, 3, 1. Now, before I even plot those points, it's important to pay attention to your horizontal or your vertical asymptote. The vertical asymptote is at 0 unless there's a horizontal shift. Is there a horizontal shift in this equation? No. So my vertical asymptote is at x equals 0. You literally get it by setting that equal to 0 or use your parent function and shift it. So I have a vertical asymptote at 0, which means my curved line is doing this. It's going to get as close as it can to 0 without touching it. And then it points to the right. So what's the domain here? Good. 0 to positive infinity. What's the range? All real numbers. -infinity to positive infinity. What's your x-intercept? 1, 0. So either from the graph or from the middle coordinate of your t-chart. Questions? Yeah. Not for logs. Yep. So just like domain never changes for exponential, it switches from the x to the y, so the domain to the range. All right, look at G. First of all, what do we know about the negative on the front? It's going to flip it upside down. What about the -1 on the inside?
It's going to shift it to the right one.
To the right one, and what else does it shift? Vertical asymptote. So if I set this equal to 0, I get my vertical asymptote is at x equals 1 this time. So before I even start, I know there's a vertical asymptote at 1. Now I do the process we just did. Change f of x to y. Before I can convert to exponential, that log must be on the side by itself. There can be nothing in front of it. So if it was like 2 plus log, I would first subtract the 2. If it's negative log, the first thing I'm going to do is actually divide or multiply by -1, and it ends up being -y. Now the 3 comes over and picks up a -y. Drops off, leaving x plus 1, and then I'm going to add the 1 at the end. And I get x equals 3 to the -y plus 1. And now I plug in for y. So 3 to the -1 plus 1, 3 to the -0 plus 1, and 3 to the -1 plus 1. -1 obviously becomes 1. This becomes 3 plus 1, or 4. 3 to the 0 is 1, plus 1 is 2. 3 to the -1 is 1/3 plus 1. And you can keep it as 1 and 1/3 because we're going to have to graph it. With me so far? Yeah? Now I plot it. So 4, -1 is the first one. I go to the right 4, down 1. 2, 0 is the second one. It is also my x-intercept. And 1 and 1/3 1 is the third one. Now, normally our graph does this, but we have a negative on the front, so it makes sense that it is coming down like this. What's our domain? 1, positive infinity. Range? Negative infinity to positive infinity. Our vertical asymptote we already got, and our x-intercept we already got. Questions? You do this one. All right, so the first step is to change the f of x to y. Then the 4 comes over and picks up the y. So it's 4 to the y equals x minus 5. And then we're going to add the 5. So that 5 comes after we plug in for the exponent. Then we go exponent, then we plug in, sorry. Negative 1, 0, 1. So 4 to the negative 1 plus 5 is 1/4 plus 5, or 5 and 1/4. 4 to the 0 plus 5 is 1 plus 5, which is 6. And 4 to the first plus 5 is 4 plus 5, which is 9. Where's your vertical asymptote this time? X equals 5. So all the way over here is where we're starting. So 5 and 1/4, negative 1 makes total sense. 6, 0, which would be your x-intercept. 9, 1. Domain 5 to positive infinity. Range, all real numbers. Vertical asymptote x equals 5. X-intercept 6, 0. Questions? So on your quiz, you'll get at least one log graph like that without a calculator, and one exponential where you're going to get the graphs and then the t-chart and then all the little parts in between. Okay, the rest of it is a lot of the like log and exponential stuff. We're good? Okay, so the last part of this is natural logs, and just like we did with exponential functions, we got a natural base, that's e. If you're finding the log of that natural base, so log of e, it's called a natural log. So when you see ln means log base e. Just like log means log base 10, ln means log base e. If you are going to do a graph of ln, it's going to look very similar to graph of 3, because it'd be like the same thing as doing ln, or log would be the same thing as doing log base e, and then it's the same thing as, or similar to having a base of 3. You won't do ln graphs without having a calculator to figure out your points, because you're not going to find e to whatever power it is. But they do take on all the same characteristics as your log graphs. And then you get a bunch of mental math stuff with ln, because if ln e happens, then it's just the exponent. So if I had ln of e, it's 1. If I had ln of e squared, it's 2. ln of e to the third, it's 3. So that kind of stuff is also fun and easy mental math. The calculator part, you'll literally just plug in. So it says use the calculator to evaluate the function at the indicated value. Round your answer to 3 decimal places. So we're doing 2 times ln of 12.5. ln is the same button that we used yesterday for the e, only we don't hit second. We do 2 ln 12.5. And I get 5.0514, which means we don't round up. We just keep the 0, 5, 1. So again, calculator use probably not on the quiz, but you will see it like heavy, not heavy, but a good portion of it on your test. All right, these are our easy mental math ones. So if it says ln of e, this is like saying log base e of e, and anytime the base on the log and the exponent are the same, right, it's just 1, because it would be the exponent on that value. So I don't even have to go that far. I could literally say ln of e is 1. Negative 5 times 1 is negative 5. So again, if it was like ln of e to the 7th, it's 7, because ln of e would cancel out to give you the exponent. And the reverse of that, if it's e to the ln of 7, that's like saying e to the log base e of 7. Now the base on your exponential function is the same as the base on the exponent, which means I literally cancel out and it's just 7. So there's a lot of questions in the homework, but a lot of them are like that. Like they're quick, easy. So don't get scared by the count. All right, now we're going to graph the ln. So in order to do this, you would have to have a calculator of some sort, whether it's a scientific or a graphing one, but you'd have to have it. But they take on the same characteristics of a log. So without a calculator, you should be able to tell me where the vertical asymptote on this is, which is what? X equals 3 is my vertical asymptote. Okay. Without a calculator, you should be able to tell me my domain is 3 to positive infinity and range is negative infinity to positive infinity. So now when I rewrite this to get my equation, I would get y equals log base e of x minus 3. Then the e picks up the y. And then e to the y plus 3 is what x equals. So you can even find some of these points without a calculator. Some of them. You won't have to, but yeah. So 0, e to the 0 plus 3 would be 1 plus 3 or 4. And what is e to the first? 2.7 plus 3 is 5.7. So you don't even need it for those. Obviously, I wouldn't expect you to have to do 1 over 2.7. But e to the negative 1 plus 3 is that. This, I would say, you use your calculator, e to the negative 1 plus 3, which is 3.36 or 3.4. Questions? Okay. Web assigned homework is open. Like I said, there's a lot. So the mental math ones, I don't even need to see work for some of those. Obviously some do, but not all of them. But the graphs, you need to graph by hand. Like even if it's an LN graph, you're going to set up your T-chart. Because you would have a T-chart on a test if it was an LN question. And then the graphs of all the logs, you want to make sure that you, whether they're multiple choice answers or not, that you are graphing them by hand and then selecting it. This is the last homework of the first quarter. Wait, is that right? No, Mondays. Yeah, but I might give, Mondays would be the last homework of the third quarter. I mean, of the first quarter. And I think I said it, but I'll drop your lowest homework grade, but I'm going to wait till they're all graded before I do that. So that will happen after Tuesday.